So let me explain what's happening in these traces here. What we can see up here in A are current responses. So these are the currents recorded in the cerebellar Purkinje cells in response to these voltage steps here. So what you typically do is you start off at a low voltage. Here it's minus 100 millivolts, and then they're doing small steps for 50 milliseconds to another more positive voltage, and then returning back to minus 100 millivolts. And these are the responses that you see, the currents that you see in response to that. So just taking this through step by step, for very low steps you would see not very much, probably this trace down here. But then as this voltage gets progressively bigger during the 50 millisecond step, you're getting bigger and bigger inward currents, which are transient, so they're decaying back to the baseline. And then you reach a point where you get the maximum response somewhere along here. And then at this point, all the sodium channels are open. So from now on, the increase or the changes in the current are not due to the probability of the sodium channel being open, but due to the passive properties, the ohmic conduction rules based by Ohm's law. So now as we're getting more and more positive still, what's happening is that the currents are getting smaller, not because there are fewer sodium channels, but because we're getting towards the equilibrium potential for sodium. So what they're showing here in B is simply one example of those traces. And then in C, what they've done is they've measured the current that you get. And so one point I should point out here is what they're also showing in B here. You'll notice that this current is not going back to baseline here. So this here is actually the persistent current. So what they've done in C is they've taken the response to a step to minus 25 millivolts, measured the size of that current. So you get the current, then you divide it by the capacitance here. So that's current divided by capacitance. Dividing by the capacitance normalizes for the size of the cells, because if you've got a cell that's twice as big, you're going to get twice as much current for the same channel density. So by dividing by the capacitance, you're effectively dividing by the area of the cell, because the capacitance is proportional to the area. And this is what they're showing here. And then in the middle traces, they're doing in the presence of the CAM-K2 blocker. So basically what they're showing by looking at these traces here and the effect of the CAM-K2 blockers, they're showing that this peptide, by blocking CAM-K2, is also blocking the size of the persistent current.